very simple and relatively uninteresting chemical reaction equation. You know that chemical reactions are generally written as equations. Sometimes you can put the state of the substance. You don't always have to, but I thought for this one we would. So CO2 does combine with water. Not very easily, but it does. Put it under some pressure usually. This is an equilibrium, so instead of yielding the product, make that one a little heavier, there's a chemical equilibrium. It's a reversible equilibrium between the CO2 and water and carbonic acid. You don't need to know carbonic acid necessarily. So carbonic acid dissociates right away into carbonate and bicarbonate in water. But for this reaction, this would be at least the immediate products. So on this kind of the side of the arrows, the product, these then are the reactants. We call these the reactants. You know this? This sign, I drew it a little weird. This represents that this is a chemical equilibrium. Very high. And remember what an equilibrium means. It means that it's reversible. The ratio of the reactants and products is constant. This reversible reaction. So, just an idea that's a chemical reaction, right? It's an equation. Another one that possibly slightly more interesting, still involving the small molecule CO2, since we know the structure of that one, and I'm not putting the states in anymore. And hydrogen gas, this is a little more interesting. This is a reaction that actually yields products. It's an irreversible reaction. And the products are these molecules. So this is a molecule called formaldehyde, a very simple organic molecule. Water, you know water. And this is, you already know, this is carbon dioxide. So there's some chemicals that you see over and over again in biology, like carbon dioxide, that I would expect you to know the name and the structure of there. Now this is different from this reaction. This happens spontaneously. Not to very much a high degree, but a little bit of this product is produced when you mix these in water. You could push the equilibrium in this direction by applying pressure, but it does happen spontaneously. This does not happen spontaneously. We would say this is a non-spontaneous reaction. And you may remember from studying thermodynamics in chemistry, that means that it's going to require some energy input. Energy can be applied in the form of heat or other forms of energy, as we'll see. But it takes some energy to make this reaction go. So while we will be talking about chemical structures and matter a lot in biology, we'll also be discussing the energy conversions a lot. It's an important part of what we'll be doing. And so I want to talk a little bit about energy. This is, again, as a review. Matter of fact, I'll write it because I have this on the slide. This was in your chemistry review from the lab manual, too. This idea of energy. You can talk about energy as the capacity to do work. There are different ways to define energy. But importantly, we will always talk about two categories really of energy. Kinetic energy, the energy of motion, and the other being potential energy, which is stored energy due to position or location. A lot of time talking about potential energy in particular. So remember, simple diagrams like this, you remember that this dot is a water molecule at the top of this waterfall, that it has a higher potential energy at the top than it does at the bottom. And as it's moving, that energy will change. So position or location, potential energy. We also can talk about potential energy of electrons. So this is most of what we'll be talking about. We will not be placing things at tops of waterfalls. It's not a physics class. Right? What we're going to be doing is considering electrons, whether they are near the positively charged nucleus in a lower energy orbital or out in a higher energy orbital away from that nucleus. So when we're talking about energy in this context, we'll be referring to chemical energy. The chemical energy of molecules. Asking questions like, how much chemical energy is in that molecule? What is the change in the chemical energy from the beginning of the reaction to the end? So we define this chemical energy as the potential energy, so it's a type of potential energy. So it's potential energy, we'll say, of electrons in chemical bonds. I'm writing in columns. I'm always good. So, in other words, the energy to the position or location of the electrons, whether they're close to the nucleus or not close to the nucleus. We will be considering this potential energy. So, because we're going to be talking about energy conversions later on, we'll be talking about how if you have an electron that's at high potential energy, one of these high potential energy orbitals in the higher potential energy shell, if it falls to a lower potential energy, that's an energy transformation. And that can be converted to kinetic energy, as we'll see. But mainly we're going to consider the potential energy of electrons this way. Now, when you see a cartoon like this, with just, just the nucleus of a single atom, and you can imagine these different energy shells, the electrons that are farthest away from the nucleus, those are at higher energy. And that's easy to imagine. It's a little harder to imagine the potential energy of electrons in chemical bonds, because you can't depict those chemical bonds as hybridized bond orbitals as well. So let's go back to this equation here. Instead of writing it as an equation, let's look at the chemical structures. So we have carbon dioxide, you know that one. It's one of the structures you should know. And actually, I'm not going to do the whole equation. I'm going to worry about hydrogen. Let's look at the difference between carbon dioxide and formaldehyde, which is what the carbon has been converted to, this type of carbon compound. So if we consider the difference in potential energy between carbon dioxide and formaldehyde, here's formaldehyde, a structure you may not be familiar with. It's a very simple structure. It's formaldehyde. Combine it with hydrogen. So if we think about the electrons in the chemical bonds, what do you know about the electrons in the chemical bonds of carbon and oxygen bonds? What kind of bond is that?
Double bond.
It's a double bond, but it's polar, right?
Mm-hmm.
Polarly polar. So where are the electrons? Closer to carbon or oxygen?
Oxygen.
Oxygen, yeah. So for both of these bonds, we have the electrons, those 4 electrons over here, being pulled closer to the oxygen in both directions. Now if we consider formaldehyde, formaldehyde still has one carbon-oxygen bond. But remember, carbon and hydrogen have pretty much the same very low electronegativity. So neither of them has a very strong pull on the electrons. So what that means is those electrons are actually at higher energy. They're one of those outer orbitals compared to where they were when they were held close to the oxygen. Now they're farther away from the oxygen. I can't really draw it. But we'll just put the little dots on the bond here, showing that they're about halfway through. Look, I'm dividing hydrogen by carbon there. I know those lines already represent the sharing of electrons, so those are just little cartoon electrons there. To make this point, it's a way of illustrating this idea that these electrons, the ones that are when carbon is associated with oxygen, these electrons exist at lower potential energy orbitals. They're lower potential. PE for potential energy, by the way. Potential energy. PE. Because I get tired of writing potential energy out. That's terrible. PE. Potential energy. Not physical education, that's a different kind of PE. It's potential energy. So these are at lower potential energy. Their location is closer to the nucleus of the oxygen. They're being pulled to get closely and kind of held tightly and safely there by the oxygen. They're not very energetic. Whereas these electrons, now the ones that have been carbon and hydrogen, these electrons are now are located, or they exist at much higher potential energy. They're in high potential energy orbitals. So in this transition that occurred in the course of this reaction, we've gone from electrons at low energy to electrons at higher energy. Those electrons have boosted to higher chemical energy. And we say formaldehyde has more chemical energy than CO2 does. That's why it requires energy input to make this reaction go. You require some energy to push those electrons into higher energy orbitals. And we'll talk about how those kind of transformations happen when we discuss metabolism, but for now I want you to understand this idea of chemical energy differences in molecules. So, of course, the type of molecule we're mostly talking about are these organic compounds. It's an organic compound. And I've said that organic molecules have carbon, and that's true, but most of the time CO2 is not considered to be an organic compound. It's tricky. I know it contains carbon, but this carbon is oxidized. This is not high, it's very low energy. So you can't build anything with it. You can't get any energy from it. So generally when we define what organic molecules are, organic molecules are those that contain reduced carbon. Reduced carbon has energies, has electrons at these high energy orbitals. So consider methane. Our friend methane, our simplest, easiest to draw organic compound. If we consider where the electrons are in all of these bonds, they're all in nonpolar bonds. It's all bond between carbon and hydrogen, so they're held in those high energy orbitals. Think of them as being equidistance between the carbon and the hydrogen. Just kind of stretch your thinking a little bit. Think, okay, that means high energy when they're halfway in between. So these are all nonpolar, and therefore high chemical energy bonds. High chemical energy, if you specify, I mean chemical energy, I'm talking about the position and the location of their electrons. Okay. I mean that in a very specific way. So not only are these these organic molecules with their carbon and hydrogen bonds, not only their electrons are at high energy, but if you look at this from the perspective of the carbon, compared to the carbon situation in CO2, let's compare them here again. I've drawn CO2 a lot of electrons. So CO2 compared to something like just a carbon compound, something like this. Just one. Any molecule with reduced carbon has at least one of those bonds. The electrons here, I should have drawn one of these. As I said, these are low potential energies, these are higher potential energy. But if you're this carbon, if you're that carbon, those electrons have been pulled away from you. If you're this carbon, now you've gotten them back. They're closer to you now. You have more electric charge density. So we say that in this case, in this particular instance, here, this carbon has gained electrons, is reduced. This carbon is lost them basically. This is oxidized. So this brings us back to something we may need to review. Oxidation, reduction. Your favorite part of chemistry, probably, I'm thinking. Who doesn't like redox reactions? Everybody likes them. So, just a quick review. I spit it over here, I don't know. Of redox. We use that term redox, but you know when you write it out, you always write out oxidation, reduction. Reactions. How do you call it? It says reactions there. The word reaction. Put the screen up, but it's too much trouble. So you don't say oxred. You always write it oxidation reduction, and you say redox. I guess it just sounds better that way. And you know that these are reactions that involve the loss or gain of an electron, or more than one electron sometimes. So loss or gain of an electron. Probably the simplest example when you've seen in inorganic chemistry is a good one to use here to remind you what this is about. Something like iron. Iron can be what we call an electron donor. It can donate electrons, whereas copper 2 plus, can accept electrons. So we say it is an electron acceptor. It's the word acceptor written badly there. Right, so anyway. I don't know if that's going to help. Electron acceptor, we'll see. So, in a redox reaction, electrons from the electron donor, iron here, are transferred to electron acceptor, and that means that the electron donor becomes oxidized, so it's lost electrons, and the electron acceptor becomes reduced. It gains the electrons. So we use these terms, oxidation and reduction, to say iron here is oxidized. It lost electrons. So we could define that. Do we say, some room over here, copper
Been reduced.
is reduced. So copper, iron. Over the course of this reaction. So this term, oxidation, right, I'll come back over here and write it. Oxidation, the noun. We can define that then as a loss of electrons. Iron started out with electrons, now it has fewer, it's lost its electrons, it's now positively charged. And you could then define reduction as a gain of electrons. Remember why we call that reduction? Because electrons are negatively charged. If you gain more of them, you become more negative. A reduction in your charge, right? A more negative atom. So that's why it's called reduction. But the reason this is called oxidation is different. Because there's another way an atom can become, or a molecule can become oxidized. Go back over here. The way this carbon has been oxidized is it's been combined with oxygen. And oxygen will steal your electrons. So if you're in a bond with oxygen, oxygen takes the electrons and you're oxidized. You lost them. You haven't lost them completely, but you kind of lost them. You've lost control of them, think of it that way. So we can also define this, rather than just saying loss of electrons, you can also say a gain of oxygen. Something is oxidized. Remember how electronegative oxygen is. Oxygen goes around stealing electrons from everything all the time. That's why things rust, because oxygen is taking the electrons. Oxygen is taking your electrons right now. It's dangerous stuff, oxygen. It steals electrons. You combine something with it, that element becomes oxidized. Another way you can say something has been reduced, in this case, this carbon is reduced because it gained a hydrogen. And hydrogen, remember, is not electronegative. Hydrogen can't hold on to its electrons at all. So if you can combine with hydrogen, you can steal hydrogen's electrons. It's very easy. You can barely hold on to them, so you can take them if you're a carbon or something else. Then you have to be very electronegative, right? So another way that you can talk about reduction then would be a gain of hydrogen. Now keep in mind, I mean gain of hydrogen and its electrons. And there's a little dot there to remind you that's not a hydrogen ion, that's a hydrogen atom with an electron. Now, it's not stolen them completely, and they're not closer to carbon than they are to hydrogen. It's still a non-polar bond, but they're closer to carbon than they were. Goes from oxidized to reduced. And so we've already talked about the fact that once carbon has gained the electrons and carbon here is reduced, these reduced bonds, these reduced carbon, this reduced carbon here in these bonds has those electrons at high potential energy. So reduced carbon has more energy. I do have these pictures to put up on Canvas. Little pictures of the high energy position here. That's an old textbook that used to show this. See if you can review that idea. So that if you look at methane and oxygen, it will not do. You can combine methane with oxygen, and then that carbon would become more oxidized. Let's go back to this equation.
So when the carbon becomes oxidized, then it has lower potential energy than it did previously.
I'm sorry, say it.
So it would have lower potential energy than it did
Exactly.
previously.
It becomes oxidized. And this is basically, in a nutshell, how we use things like hydrocarbons and any kind of organic molecules for fuel. We combine them with oxygen and try to capture that capture that energy as those electrons are lowered. So, in the case here, the carbon dioxide and water, carbon dioxide and water end up, let's do this. Get rid of these boring equations here. We'll use that one. The one I had written over here before, which was the carbon dioxide, but I've written in structures like I did there, combined with hydrogen gas, and that yields, once you add enough energy to move the electrons to higher energy orbitals, that'll yield the formaldehyde and water. So look where the oxygens are, and I don't know why they made that water linear in that molecule. It's kind of a weird picture. Use that. So where are the electrons? At the beginning of the reaction, the electrons are held close to the oxygen, low energy. Hydrogen and hydrogen, of course, are holding them equally. That's a bit some energy there. This is a reduced. But then the carbon here is more reduced compared to the carbon here. Now, still, some of those electrons are held by the oxygen, right? But this is still going to be a molecule that has two high energy bonds and it's more reduced relative to CO2. It's less reduced relative to the electron. Methane. Methane is the most reduced there. So of those three molecules, carbon-containing molecules, CO2, and formaldehyde and methane, which has the highest chemical energy? What do you think?
Which one? Out of these two?
Comparing the carbon compounds, we have CO2, we have formaldehyde, and we have methane.
Oh, methane?
Who says methane? Just agree, she's right, it's methane. Being shy, see, afraid to be wrong. Don't be afraid to be wrong. Why is it? Because all the bonds are non-polar. They have more chemical energy compared to just having two bonds non-polar. And of course, the electrons here, to finish this reaction in water, now compared to where the electrons were in hydrogen, okay, hydrogen has been oxidized. So here, hydrogen is oxidized in the course of this oxidation reduction reaction, and here the carbon in this formaldehyde is reduced. So we'll see some examples of these kind of reactions in metabolism, but we'll also, when we start talking about our different kinds of I had this on the board too. We'll talk about different types of compounds, and you'll be able to see that some of these compounds have more chemical energy than other types of compounds. It will be clear. Organic molecules with those reduced bonds, that's why we consider this to be not really organic. It's just low energy. So at the end of, I guess we had a lab last time. When did we do that in that very long day? I can't remember. We just talked a little bit about hydrocarbons. We went through methane and ethane and propane, right, and butane. So those are hydrocarbons. And remember that all of these, even though I'm drawing all of these, like the methane I had already that I've raised here, I'm drawing them flat because it's easier to draw it that way. All of them are going to have this tetrahedral bond shape because that is the tetrahedron that you get with each time carbon makes a bond with anything, basically. So these are not really going to be flat. Now the first type of molecules that we looked at were the hydrocarbons. So we're going to be talking about types of organic molecules, and this will take us all the way into all the way through chapter 5. We're going to spend a lot of time in chapter 5. It's not that long of a chapter, but we're going to look at these molecules in a lot of detail. So far, we've just seen the hydrocarbons. That was in chapter 4. And remember, the hydrocarbons, our first type of organic molecule, are these like propane and butane, those are not really biological molecules, those are the remains of biological molecules. Those are the carbon skeletons. They just have carbon, just carbon and hydrogen only. That's all they have. That's why we call them hydrocarbons. So these are fossil fuels. In other words, these are fossils. These are what are left over after the other biological molecules, like carbohydrates, lipids, and proteins, after they've been under pressure for millions of years. All the other elements, the oxygen, the nitrogen, phosphorus, the other elements have been basically knocked off, and you're left with just hydrocarbons. But hydrocarbons are not part of this. They're not really in by themselves in organisms. Okay. So the ones that are in organisms, we're generally going to refer to the biological molecules, the large biological molecules that make up about 96% of us, even more. And the biological molecules, we're going to start today with carbohydrates. It's a class of biological molecules, the carbohydrates. We will talk about the lipids, things like fats and oils. We will discuss in detail proteins and their structure and their functions, a really big molecule. And finally, a group we call the nucleic acids. This is all what chapter 5 is about. Now, there are lots of other types of organic molecules that don't fall into these categories, but this is not a course in organic chemistry, so we won't be talking about those, not really. Just hydrocarbons and then the biological molecules. So to get all of these, you start with these carbon skeletons, carbon chains, and you've got to add other elements. So we add those in the form of what we call functional groups. These are chemical groups, chemical groups that contain other than just carbon, basically. Two carbon chains, sometimes carbon rings. So we talked a little bit about just the diversity of hydrocarbons. These are all these molecules just have carbon and hydrogen. You recognize some of these as being fuel. We will see that some of the branch structures and some have double bonds, but some actually form ring structures. The rules for drawing those are a little different. Here's a ring structure, which is just hydrocarbon.
Benzene ring.
You know this one? You know this one?
Benzene.
Benzene ring. Right? And you can draw it like this to show the carbons, the single bonds, the double bonds, and all the possible hydrogens, and you make sure that you have 1, 2, 3, 4 bonds around each carbon. But you probably know that you often see them drawn like this. So here's a benzene ring. This is different. In this type of structure, the carbons are just implied. It's a corner, so it must be a carbon. If it was some other element, it would be something else. We'll see examples of this. Or that. If you have something that's not part of the ring structure, then it's out on a line there. You don't put the hydrogens in these because that, if you put any extra bond or line there, that would imply carbon. These hydrocarbons, I can't remember where I showed you this slide or not before.
Yeah.
Did I know?
Yes.
I did? Okay. So you remember they're nonpolar, they don't dissolve in water because water's hydrogen bonding to other water. So it just excludes these into the middle. We'll talk about this more. This is called the hydrophobic effect when we talk about things like lipids, which are very nonpolar. Talk about this hydrophobic effect. So the water molecules are binding to other water molecules, and so these nonpolar ones, octane, here's these hydrocarbons, they're excluded kind of together. But once they're together, they can get close enough to attract each other very slightly. Remember what kind of attractions hydrocarbons might have to each other?
Dispersion.
LDF.
Van der Waals interactions, right? So I put these notes in here. They're mostly from the handout, but they're similar. But remember, even though they're neutral atoms in nonpolar bonds, you have these momentary shifts in electron density. So normally, it's just here's the electrons kind of evenly distributed around the positive nucleus. But they can be, this circle represents the electrons. They kind of shift over here for 1 second, less than a second, nanosecond. There can be more electron density on this side, or in the next nanosecond, there could be more electron density on the other side. So as they're vibrating back and forth like that, you get this shift in density. If you have two different atoms, usually what happens is once one starts vibrating, it'll make the other one start vibrating, so they vibrate synchronously. And now this for an instant, for just an instant, you have a partial negative charge and a partial positive charge next to each other in those two atoms. And each of those atoms would be on a separate except for non-polar bond. And in that instant, they're slightly attractive. If this is going to change, it's going to go back, right? It's just vibrating back and forth. These are not permanent dipoles, not permanent partial charges like we have with polar bonds. But it's a weak interaction. You should know that van der Waals is the only thing that can attract non-polar bonds together. And it's not very strong. So we have something like these hydrocarbons, these are film, what do you call it, space-filling models of hydrocarbons. It's just carbon and hydrogen there. Here's an 8-carbon one, here's a 6-carbon one. The only thing that holds them together is this slight shift, and the longer they are, the more likely they're going to hold together. Remember, we talked about how that gives it just more opportunities for van der Waals interaction. So it's kind of a zipper effect. You have a lot of them. Sometimes you may have heard these called induced dipole. If you want to think about something you might have learned in chemistry, that's what you're going to call that. All right, it's just a quick review of that when you see these. Now, what we're going to do now is we're going to build something other than hydrocarbons, because I think we're done with hydrocarbons. Okay, that was organic chemistry 1. And for organic chemistry 2, or actually no, we'll finish organic chemistry. We can go straight to
Biochemistry.
biochem, I think. Well, actually we have a little bit of organic chemistry to do before we get to biochem. And that is the different kind of functional groups. So, these functional groups that we're going to add to the carbon chains to make these different types. So before we start talking about these individually, I'm just going to go through all the different types of functional groups. These are all consist of bonds that you've already seen, mostly. Maybe a few you haven't. So you should be able to look at the bonds and give a pretty good idea of what the properties of the groups would be. These are not really in any particular order, but I'm just going to number them because I like to number things. So the first one is one you've seen a lot. You might not have named it this. It's called a hydroxyl group. And that's when you have attached to your carbon chain, so I'm not going to attach that bond to anything, an oxygen and a hydrogen. Remember, oxygen can make 2 bonds, so just bonds. So, of course, this is very familiar to you. You know that this is a polar bond, right? Partial negative associated with one end of the bond, partial positive to the other. When we draw this as a group, as a functional group, very often we will draw it, or we'll just draw it like this, an O and an H. You saw that in the handout. That was done in those sugars. So this implies that there is a covalent bond between them. It means the same thing. It's just kind of shorthand for that bond. So, obviously polar. So this is a polar group because it's a polar bond. And you know, anything with a polar bond can hydrogen bond with water, which makes it hydrophilic. So when you see this group as part of a molecule, you'll know that at least that part of the molecule is hydrophilic. It means it's going to be water soluble, or the water will at least stick to it in that area. So simple molecules that have a hydroxyl group like this. I can put the hydrogens in here or not. You know, they're optional in there. You know this one?
Methanol.
Yeah, methanol. And this one we've already seen. I'm gonna leave the hydrogens out here for clarity. Ethanol.
Which is used to make alcohol drinks.
So, you'll notice a theme here in the naming, OL ending. That means that the main functional group was functional group.
Is an alcohol.
It really decides the characteristics of the organ of the molecule is a hydroxyl group. So we refer to these in general as alcohols. So this would be a different type of organic compound than hydrocarbons, and not one of our groups. So we really won't be dealing with these very much. We'll see some alcohols in action. Another alcohol, overall what they are. Another alcohol that we'll see later on. This one, I'm used to drawing this vertically. It doesn't matter which direction you draw it in. It's just a habit. And this is an alcohol that has not just one hydroxyl group, but 3 attached to each one of the carbons in this 3-carbon molecule. This is glycerol. And we'll see that glycerol will be one of the components of some larger molecules, some of the fats. We use glycerol to make fats. So this alcohol, we can consider this a class of organic molecule. Anything that has the OH group, the hydroxyl group. So one of the things that you may need to do in recognizing functional groups and their properties is you may be asked to identify a functional group. This is how you do it. circle this functional group and say, oh, hydroxyl group there. Circle and label is a handy thing to be able to do. It's a hydroxyl group. And that means that these are water-soluble molecules because they have it. The next group, by the way, I just had this slide up there because it's another excuse just to have a picture of the Jesus lizard. Have fun. Our next group is the carbonyl group. Carbonyl. This one we also have seen as a bond. It is the bond between carbon and oxygen, a double bond, and the carbon is also attached to something else, so it would be attached to the carbon chain. And what do we know about this one? Is this polar or non-polar?
Polar.
Polar, right? Because you have oxygen, which is going to give it a partial negative on this side, and carbon a partial positive on the other. Which means that when you see this in a molecule, then you will see that that part of the molecule is polar, and then therefore hydrophilic, water-loving. Now there are two different types of carbonyls. We use abbreviations for them a little differently. One type of carbonyl, we will see, is called the aldehyde. You actually have seen that already in the very smallest version of this, which was that formaldehyde molecule. So an aldehyde, when you have the carbonyl group at the end of the chain, if you have carbon at the end of the chain, then you have the carbon double bonded with oxygen, but you also have a hydrogen to fill the octet role for carbon there. So, it's at the end of the chain. Did you notice this one only had 3? You're attaching it.
And we have a ketone.
And so the aldehyde, this means it's at the end of the chain. You have it. Sometimes this is abbreviated CHO. And obviously, this abbreviation doesn't represent the shape or the structure of that group very well. It's just an abbreviation, so you know what it is. But if you're drawing a structure, you want to draw it out. So an example we've seen already. When you have just the smallest one possible, when the whole thing is just one carbon, then you can just have the one carbonyl group. And we've seen this one. This is formaldehyde. Formaldehyde is an aldehyde type of group. And then a slightly bigger one. You have 2 carbons. The last carbon, the one at the end, is a carbonyl group. It's just hydrogens, which I won't draw in. This is a molecule called acetaldehyde. And we'll see that acetaldehyde is an important intermediate in some metabolic processes. Things like the breakdown of alcohol, the metabolism of alcohol in the body. But again, that is the aldehyde group, the carbonyl group at the end there. And you can tell by the naming that if the main functional group of a molecule is an aldehyde group, we call that an aldehyde. The class of compounds would be an aldehyde. And as I heard somebody say, the other type of carbonyl group is called a ketone. So ketone is when you have the aldehyde group in the middle. So the carbon is attached to something else. So it doesn't have to be exactly in the middle of the chain, it just can't be on the ends. Anywhere not on the ends. But we're going to say, to make it easy to write, we're going to say at the middle of the chain. So with a ketone, if the carbonyl has to be in the middle, what's the smallest ketone you can make?
Acetone.
Acetone. So how many carbons?
3.
3, exactly, because you have to have a middle of the chain. The only other middle is to have 3. So then here's our ketone. Yes, these are hydrogens. So acetone. You notice the O-N-E ending. That's telling you that's a type of ketone. If it has a ketone group, we call it a ketone. Acetone is something we will use in the lab, but of course it's not part of organic compounds. But we'll see aldehyde and ketone groups as a part of other biological molecules that have other functional groups as well. The carbohydrates, as it turns out, we'll see those in a minute now. So, the next type of functional group. a carboxyl group. Carboxyl. I know that looks a lot like carbonyl, but it is different.
Nope.
The name kind of implies what it is. It's kind of like a carbonyl group with a hydroxyl group. They're both. So essentially you have carbon attached to your chain, and you have the carbonyl part of it, and then you have the hydroxyl part of it. But when you have this combination, we now call that a carboxyl group. So there are some shorthand ways to write this. Instead of writing all the bonds out there, you might see it, and I'll often use this shorthand where I'll go ahead and write out the carbon double bonded with oxygen, but then I'll write the hydroxyl group like this. It's a common way to show it in the structure. Probably the most shorthand way is just to write COOH. And again, that abbreviation doesn't tell you how the atoms are arranged, but it's useful. It's useful to have. You're talking about it. So in this case, we actually have two polar groups, and they're very polar, particularly this one. So this is polar, right? You have a partial positive by the carbon, partial negative by the oxygen. But because this is right next to this very polar bond, this is the most polar of polar bonds, it makes this one even more polar than a normal hydroxyl group would be. It's special, so this is very, very polar. Here, so this is a very polar bond. So much so that that bond becomes ionizable, which means that this can act
That's a weak acid.
as an acid, as a weak acid. It can lose that hydrogen ion. So here's a very small example. A molecule, I'll draw it all the way out like this. Molecule with a carboxyl group. You know this one?
Acetic acid.
Acetic acid, yeah. I used this as an example before when we were talking about weak acids, just differences I didn't draw the structure out. So this is a very polar bond, so this is a very negative, very positive situation here, and what can happen, I'm not going to put the water in the equation, but when mixed with water, it can lose this hydrogen completely because the electrons are pulled so close to the oxygen that it loses control of them, and then you have an anion because what's left is the oxygen. And the oxygen keeps all the electrons, so it has a full negative charge, and the hydrogen is released as a hydrogen ion, proton. So hydrogen ion, really a hydronium, right? And an anion with -1 charge. So this, you're going to see molecules that have this type of carboxyl group. And so the ionization state, whether it's protonated like this or ionized, will depend on the pH of the solution. How many hydrogen ions are around, because this is an equilibrium. Okay? So another example, a very small example of a molecule with a draw like this. So approach its shape. There. That's a molecule. The whole thing is just one carboxyl group, really. This is called formic acid. Hopefully you've not really come across a formic acid too much in your life. I have, because I'm from Florida. See, around here, you know, even ants, there's a lot of ants. There's little black ants, very nice. You can pick them up, they can crawl in your hand, no problem. In Florida and other places in South America, they have ants. We have red ants. And red ants will inject formic acid into you, which is really much more painful than a mosquito bite. It's really nasty. Some people have allergic reaction to it, but it hurts everybody. So formic acid is an example, another example of a molecule with a carboxyl group. So we refer to these kind of molecules that have the carboxyl group as their main functional group. We say they are organic acids. Another type of organic acid that we'll talk about soon is something called a fatty acid, which is a long hydrocarbon chain with a carboxyl group. That's an example of organic acid. And there are others. Yes?
What's the treatment for that for formic acid if you did find it?
I don't know. Maybe they have a treatment for it. My mother just says stick it in the ocean. Stick it in the pool. On the moon, I mean. I don't know what you can do. crying. When your kid get bites on your toes and on your feet when you're a little kid. Just crying. I know. I haven't been bitten by, or stung, I guess, by a red ant in many years. Luckily. All right. So I'm numbering things. I'll keep numbering things. So this next one is, again, bonds you've seen before. This is the amino group. Amino or amine group. Wait, oops, that's not what I mean, right? Amino group. So finally, we're going to add some nitrogen. So far, it's just been carbons and oxygens and hydrogens. This is how we're going to add nitrogen. So nitrogen, you may recall, has 5 valence electrons. So it can form 3 bonds, and it has these 2 non-bonding electrons. It's very electronegative. So this is going to be a very polar bond. Not as polar as a hydroxyl group, but pretty polar. This is negative, but we do have those non-bonding electrons. And it turns out that that gives this kind of special powers too. So obviously it's going to be polar. So where you find this on a molecule, it will be hydrophilic. But also, it can act as a weak base.
Like ammonia.
Because that nitrogen can grab hydrogens. It's the hydrogen ions. Oh, another way you can, abbreviation for the amino group is just to write NH2. If it's in this form, if it grabs a hydrogen, then it'd be NH3+, as you'll see. So I'm not going to put this on an example molecule. I'm just going to use the group here because it's easier. You have those non-binding electrons, just to remind you. They attract hydrogen ions, and so hydrogen ion in solution is going to be accepted. So the base accepts hydrogen ions from the solution, right? Removing them from the solution. And now they're attached to our amino group. Let's draw like this. But they came with a positive charge. So now there's a full positive charge attached to this group. So this is sometimes written NH3+. So this would be the protonated state here. Sometimes we say this is protonated, right? This would be the base. So this is a cation. I'm going to compare it to the anion that's produced with a weak acid. So I'll give you an example of something with an amino group on it later. If you had just the amino group, the molecule would be called an amine, and we're not going to really talk about any amines here. So we'll talk about it when it's combined with something else. A couple of other. Oh, by the way, in your book, there's a chart that shows all the functional groups, what they look like if you build them with a model kit, and some examples. The example they get down here of glycine is actually not really an amine; it's an amino acid, as we'll see. So, a couple of other ones that we will see less frequently than those. One is called the sulfhydryl group. I know it's a lot to spell, sulfhydryl. But remember, sulfur is one of the elements that's found in biological molecules. And when it is, it's found in this form. So this is where sulfur, which has 6 valence electrons, form 2 bonds, unlike oxygen in that way. We're in the same group as oxygen. Sometimes we just write this, let's write it simply just as H. Sulfhydryl group. This one, in terms of its polarity, it's not very polar. It doesn't make real hydrogen bonds, so it's usually considered kind of nonpolar. It's not something we need to worry about, really. Considered kind of non-polar bond, very polar. So if you have a molecule that has the sulfhydryl group on it, then this type of molecule would be called a thiol. This one is called ethane thiol. These are thiols. Where we're going to see this in biology is in proteins. And in proteins, what these sulfhydryl groups can do that make them so important is that they can form these very special covalent bonds with each other. So you end up having the sulfur attached to sulfur like this. Form this is a chemical reaction that has to.
The cross bridge.
Yeah, this is a chemical reaction that has to take place. They block their hydrogens. But those special covalent bonds are found in proteins. They help hold protein structures together. And those are called disulfide bridges. So I'm just putting this note in here so it's a complete list of why these groups are important, but we'll see that later on, so don't worry about it quite yet. Sure, why not? Another group?
And they hold their conformation, is that what you said?
Yes, yeah. It helps form their tertiary structures and gives them conformation. And we'll talk about that in all kinds of detail. So phosphate group. Remember, one of the other elements that's important in molecules is phosphorus. So the phosphate group has, I'm just going to draw it in shorthand here. It may be protonated, H2PO4, or because it can act as an acid, you might have just PO4. There's 2. We'll see. This is polar, meaning that it makes the molecule hydrophilic, but it also acts as a weak acid, which means it can lose the hydrogen ions. So, I know this looks strange, but it turns out that phosphorus has 10 valence electrons, and so it can form up to 5 bonds. So the group, I've written myself down into a place where you're not going to be able to see it there. Let's put it up here. See people doing this, like I can't see below that. I'll just continue it on this board. I'll just go up there. So, if it's in the protonated form, then you have, remember it's attached to something else. You have a phosphorus that is surrounded by oxygen. One of those oxygens is double bonded to the phosphorus, and the other 2 are basically hydroxyl groups. So this is the H2PO4. So you're supposed to have 5 bonds. There's 5 bonds around it. This can act as an acid. And then depending on the pH of the solution, that was very badly drawn, you have an equilibrium with this form. So one or both, often both of the hydrogens can ionize, and so this would be now an anion. I'll just start with both of them, and we have the 2 hydrogens that have been released into the solution, so it's acting as an acid. So we're going to see these in we will see these in nucleic acids, part of DNA and RNA. They have phosphate groups in them. We'll also see it in ATP. You remember ATP is the immediate energy source for cells, and and then another molecule called phospholipids. So a couple of places where we'll see phosphorus, and it'll be in the form of phosphate groups. Finally, there's one more functional group. It's really not the same as these other ones. All these other ones we've added some other element to, right? There's been nitrogen or sulfur or something, or oxygen. There's one other that's considered a group because it does add specific characteristics to a molecule, and that's the methyl group. And I think we used this term a little bit the other day in the lab when we were talking about the isomers. So the methyl group is simply this is just a hydrocarbon. So it's just a short hydrocarbon, a carbon with 3 hydrogens on it. Now this hydrocarbon can sometimes be written just CH3. It's shorthand. You don't need to draw all of that out, right? So you already know these bonds are nonpolar, right? These are nonpolar bonds. So that means this molecule will be hydrophobic. Molecules, at least the part of the molecule that has the methyl groups, is going to be less likely to associate with water. what type of interactions could form between methyl groups?
Van der Waals.
Van der Waals interactions, exactly.
Oh,
So, sometimes you'll see a molecule where maybe part of a hydrocarbon is drawn out, and instead of drawing out the whole thing there, we'll just put some methyl groups. It's a shorthand way of drawing that hydrocarbon, that all bonds. So let me give you an example of a molecule that has, I'll put it here. I don't like thiols anyway, they smell bad, sulfur compounds, they all smell dreadful. So here's an example of a molecule that we're going to see very soon. A molecule that has a carbon, central carbon with 4 different things attached to it. One of those things, this group, shorthand for it. Another group will be this one. Let's see if I drew that one protonated. So I drew that one protonated, which means my board must be kind of acidic. A lot of hydrogen ions around, so I think I should draw this one as being protonated too, just to be, chemically consistent. And then I think on this group, I'll just put this functional group in here, just for hydrogen.
Amino acid.
That's an amino acid, exactly. This is an amino acid. An amino acid is called that because it has an amino group on one side. So this group is the amino group. That doesn't write very well. The amino group. And then this group, remember that one's called?
the carboxyl group.
Carboxyl group. The carboxyl group makes it an acid, from an organic acid, so it's an amino acid. And what's this group called? The methyl group. So the methyl. So this particular amino acid, just one kind of amino acid, we'll learn soon that there are 20 different amino acids. And this is an amino acid called alanine. Alanine is the amino acid that has a methyl group. You see, there's another amino acid up there, their example for the amino group, that's called glycine. A special one because instead of having any particular interesting functional group at this position, it just has hydrogen. But it's also a different amino acid. So we'll see those, but it's an example that can show you different types of functional groups. So by looking at this, you could think, well, it's going to be polar for sure, right? All those polar bonds can be water soluble. This end of it's going to act like a base. This end of it's going to act like an acid. It's going to be a wild and crazy molecule. So your book has to have all of these vital group, phosphate group, ethyl group, all of that described in a chart that looks like that. Now, what we need to do is start putting some of these functional groups onto carbon chains and making the biological molecule. Now we're starting the biochemistry. I guess that was all still organic. But now it's biological. So the first one we're going to talk about are the carbohydrates. You guys are familiar with carbohydrates, right?
Yeah.
The bread, the pasta. I love carbohydrates. They don't love me, but I'm very fond of them. All of them. I love all of them. Never met a carbohydrate. So you're probably familiar with that as a term. You see a molecule like this. This is a space-filling molecule of glucose. And what you notice about it by just looking at the colors on the model, it's got carbon, and hydrogen, and oxygen. A lot of hydroxyl groups out there, so it's going to be very soluble. So let's talk about these. What are we talking about with carbohydrates? So this, by the way, is starting us into chapter 5. If you're keeping track, I'm sure you've already read chapter 5. You've caught up. At least the first part of chapter 5, it's about carbohydrates. So, carbohydrate. Different than a hydrocarbon. It still has carbon, but a hydrate implies water. So for each carbon, there's a molecule of water. So you could write a general formula for a carbohydrate like this. It's a carbon. For each carbon, there's one water molecule. And then you have different numbers of carbons and water molecules. These can be arranged a little differently. So this group includes things that you have heard of, like sugars, and the larger molecules that we have a general name for, the long chain ones that we call polysaccharides, like starch. The starch in the bread products, right? Those are polysaccharides. What all the carbohydrates have in common, though, is this formula. So here's a very small, I guess technically a carbohydrate, although it's not named like a carbohydrate. What they all have is a carbonyl group. It doesn't have to be the top. They have a carbonyl group, and then a number of carbon. Here's the carbon chain that we're going to attach all these groups onto. And then it also has hydroxyl groups. So for each carbon, in the middle part, each carbon has a hydroxyl group and a hydrogen, so that's carbon and water. And the very last one would have two hydrogens, because the top carbonyl group, of course, only has one. This is missing, it's not a full carbon and water up there. But it adds up to units of carbon and water. So, to identify our groups, which you always find on carbohydrates, you're always going to have a carbonyl group. This one happens to be an aldehyde. And you're always going to have hydroxyl groups. Those are the functional groups that makes this function as a carbohydrate. Now this particular one is actually, as I said, it's not named as a carbohydrate because it's short, and so I don't know why, but it's named like it's an aldehyde. That's an aldehyde type carbonyl. So this is actually a molecule called glyceraldehyde. Glyceraldehyde. It's technically sugar. This would be something called an aldose sugar, though, which is kind of redundant. The OSE means it's a sugar, and the aldo part means it's an aldehyde. It's an aldehyde type sugar. We'll see glyceraldehyde is an important intermediate in metabolism later on. This molecule does come into play in some of the metabolic pathways we'll talk about. Pretty important one. There is another one that is quite similar. I can see if I can draw it to make it look similar. It also has 3 carbons. Try to make it the same. 1, 2, 3 carbons. But on this carbon chain, the carbonyl group is a ketone, which means that the rest of the carbons are going to have, we're going to have, I gotta stop putting all these hydrogens in because it's messy. Going to have an extra hydrogen to make up for it, but it still adds up to the same numbers of hydrogens and carbons. So this one also has a weird name, even though this one is still sugar, it still has a hydroxyl group, it still has the carbonyl group, so you know it's technically a carbohydrate. It's named differently, it's got a weird name, it's called dihydroxy because it has 2 hydroxyl groups. Dihydroxyacetone because it has the ketone. It's a weird name. Again, this will be important to us later on when we learn metabolism. You don't have to know these names. Don't bother about learning those now. They're just a simple example that I can give you. This one would be considered a ketose. A sugar with a ketone is a ketose. And both of these are considered triose sugars. So 3 carbon sugars. So there's a lot of words that we use to describe sugars. Generally, these are trioses. This is an aldose, that's a ketose. You'll get used to those. OSE is the ending that you're going to see that means it's a sugar. So, these 2 are isomers of each other. You notice that?
Yes.
What kind of isomers of each other are they?
So it differs around the double bond, right? Or those like structural?
Structural. Structural.
Structural
Well, the
isomers.
structural is a different bond order, right? Up
All
here,
right.
the carbon for the double bond, the carbonyl group is up here, and now it's down here. We've actually changed the order of the bonds. Remember, geometric isomer would have a different arrangement around the double bonds. This has no arrangement around double bonds. So, structural
Structural.
isomer. And if you built this model, remember it's not flat. I'm going to draw all these sugars as flat, because that's how I draw things on the board. But remember, they have that zigzag shape. There's a three-dimensional tetrahedron around each one of those carbons. And then you have the carbonyl group, which has the double bond, which is not, you can't move it around.
I like this
So,
structure.
so let's get to some sugars that you do need to know. Now, when we're talking about a sugar like this, it's just one sugar. These are called monosaccharides. That's a fancy word. Saccharide is a fancy word for sugar. Sugar. That means one sugar. One sugar. Sometimes it's called simple sugars. One sugar. Monosaccharide. So the examples that we are going to, the ones that you need to know, are going to be pentose sugars, pentoses, that have 5 carbons, or just one pentose. You only have to know one of them. There's a lot of them, but you only have to learn one. And then a couple of hexoses, or hexose sugars. Hexoses have 6 carbons. And these are the ones that are so important in biology, probably the most important. So here's the pentose sugar. Pretty easy to draw. It's just 1, 2, 3, 4, 5 carbons. I have to count them when I draw. I'll lose track. 5 carbons. This is an aldose. Like this is an aldose. It has the carbonyl group at the end. So we have the carbonyl group. And then the rest of them are going to be hydroxyl groups. Now, this is an easy one to remember because all the hydroxyl groups are on the same side in this one, this particular pentose. And remember, it does make a difference. These are all asymmetric. Some of these are asymmetric carbons. So this is a molecule called ribose, or 5-carbon sugar. And ribose will be an important component of DNA and RNA and ATP. So we'll see ribose again later. We're going to see most of today is this sugar. Again, an aldehyde type sugar and an aldose. This has 6 carbons. This is one of our hexoses. So 1, 2, 3, 4, 5, and 6. And it matters which side you put the hydroxyl groups on, right? Because these are asymmetric carbons. So by convention, the way we draw this particular molecule, I'm not putting the hydrogens in because they take up too much space, but you know those are implied hydrogens, right? Is that for the first carbon, the hydrogen is on that side. Because that's I don't know if it's left or right, you know which way you're looking at it, right? Over there. And the third carbon down has the hydroxyl group on the other side. Always for this particular molecule. And then the rest of them, all the hydroxyl groups are on the same side for the 4, 5, and 6 carbons. So this is a molecule of glucose. Probably our most basic, the most important of the sugars, because we build everything else out of glucose. And this is also this is the sugar that your body uses for fuel making. So if you look at this, the chemical formula of this, it is C6H12O6. That's the way we draw it. We're drawing it in a linear form like this. There's
Couldn't be in a ring form.
it can also form a ring, and we'll get to some ring formations. Right now, these are just the linear forms. All of these form rings. They do. And we will form them later. How weird this looks. There's 2 important isomers of glucose that I want you to know. One of them is this. It's an isomer, so that means it's going to have the same molecular formula, right? It's going to be a different shape. One of them is, so you have 6 carbons still. 2, 3, 4, 5, 6. It's still got the aldehyde, the first carbon, and it still has this first hydroxyl group in the same direction. The third carbon has hydroxyl group the same. So far they're the same. The only place they're going to be different is this. On the fourth one, the hydroxyl group is going to be on the opposite side. This is the same one that was in your handout the other day. So for the last two, the hydroxyl groups are on the same side. So the only difference is right here. I think they were swapped the way we were drawn on that handout. I had this molecule. This molecule, by the way, you should know the name of this. This is called galactose. But it's still, if you count up all the carbons and hydrogens and oxygens, it's still C6H12O6. So, you know I'm going to ask you this. What kind of isomers are these of each other?
The diastereomers.
Diastereomers, right? Because this is the only place they're different. Right here. And this is an asymmetric carbon. This is an asymmetric carbon. This is an asymmetric carbon. As are all the middle carbons on these molecules. But we have a different arrangement around the asymmetric carbons, so these are diastereomers. Now, we didn't have a chance to build these. We didn't have a chance to build these in lab, and they don't look like they'd be that different when you have them drawn flat like this. But if you build them with the kits, you see you do get a very different shape, because remember, they're not really just going off to one side or the other. In 3 dimensions, you're going up and down from the plane of the board. Right? So they do have a different shape, glucose and galactose. But they're isomers of each other, and your body has enzymes that can take glucose and turn into galactose, and vice versa. Space for one more isomer here. Time. Excuse me. This last one is going to be a little bit different, but still an isomer of glucose. So it's going to have 6 carbons. 1, 2, 3, 4, 5, and 6. But now, instead of having an aldehyde type carbonyl group, this is going to have the ketone form. So it will be a ketose sugar. So there's the carbonyl group, which means this top carbon will have just the hydroxyl group, so the other carbon. Everything else will be the same as glucose. It's an isomer of glucose, which means that you'll have on the third carbon, you'll have a hydroxyl group on the opposite side there. And then for the last 3, the hydroxyl groups are on the same side. So you count it up. This is all C6H12O6. This molecule is called fructose. You've heard of fructose, like you might find in high fructose corn syrup. It's bad stuff. Right? So fructose is the same as glucose in that it is C6H12O6. It is an isomer of glucose. What kind of isomer of glucose is it?
It's a structural
isomer. So structural isomer of glucose. And these, I didn't write down before, are diastereomers of each other. So some isomers of glucose, they're important. By the way, I was thinking about this after we had our lab the other day. We've been talking about these structural isomers. You may have heard of this type of isomer called constitutional isomer?
constitutional isomer.
Constitutional, I think constitutional isomer.
Yes.
I'm not used to calling it that, but I think they're called that sometimes in chemistry. It is the same thing, if you were wondering. Obviously, I would call it a structural isomer because I can say that. I always go with something I can pronounce.
Are the diastereomers also called something different? Because I've heard a different name.
Possibly.
Okay.
I don't know. Yeah, I've always called those diastereomers. But it's been more decades than I like to admit since I've taken organic chemistry, so I don't know. There could be another name for it. Or maybe they just come up with another name for it. But we're going to do one more thing. I know we may go a little bit over, but hey, you're fine, right? Just go another hour of lecturing. You all right? I'm not really going to do that today. But I want to do one more thing, because we've got to get a little farther here. And that is, somebody mentioned this before, these can form ring structures, and most of the time they do. So in an aqueous solution, all of these will spontaneously form these rings. So I'm going to form a ring, and then we'll do that. So that means in everything, in cells, in the bloodstream, you have these linear, you have a really an equilibrium between the linear monosaccharides, like I've drawn them there, and these what we call ring structures. So they're linear in one moment, the next moment they spontaneously form a ring. So for us, this will be important in glucose, and that'll be the main ring structure I want you to understand. So I'm just going to redraw glucose here for a second. It's good practice since you have to know all of these anyway. So it's 1, 2, 3, 4, 5, 6. And remember where to put the hydroxyl groups on opposite sides, and the last 3 on the same side. Now, one of the things that we do, and I started doing it already, is we actually refer to those carbons by number. And the carbon that gets to be carbon number 1 is always the one closest to the main functional group. And the carbonyl is considered to be the main functional group here. It's the reactive group on this molecule. So this is carbon number 1, and then you just go down from there. So this would be carbon number 2, carbon number 3, 4, 5, and 6. You can keep track of the carbons that way. So for this form a ring structure, what's going to happen is that carbon number 5 here is going to be involved in a reaction with carbon number 1. To actually reduce carbon number 1 to form a ring. So the best way to show that, I think, you're on with, is I'm going to take this molecule and I'm going to lay it on its side, kind of, to show the shape it would form, and then we'll do the chemical reaction that forms it. So, bit of a challenge for me. I'll start over here with carbon number 1. So here's carbon number 1. I'm putting this on its side. Carbon number 1 is here. I'm going to randomly decide to write the carbonyl group in that direction. This is a bond that it can just swap around either way. Right? This is a single bond. It's not an asymmetric carbon, so it's just swapping around. Just swap that direction, and then we have carbon number 2, and then carbon number 3. I'm making really long bonds here to make it easier. Carbon number 4. This weird. Okay, carbon number 5, and then carbon number 6. I'm putting up here for a reason. Make it weird, isn't it? So carbon number 6 is not going to be part of this. Remember, I said here's carbon number 6 down here. It's not part of this process. So let's put some groups on here. Hydroxyl group. When this forms a ring, because of that tetrahedral shape, those hydroxyl groups are going to be forced either to the inside or the outside of the ring, which really means up and down from the board. Some of them to the inside, some to the outside, this one to the outside. So I'm going to put hydrogens in. Hydrogens take up too much space here. We'll point this hydroxyl group in that direction because we need it. Quite a number of bonds around everybody there. And then carbon number 6, this one down here, remember this has 2 hydrogens? Carbon number 6. So we can abbreviate this CH2OH. So this is what we've done. Line this on its side. We've got carbon number 1, which we refer to as the carbonyl carbon. Keep track of it, carbon number 1. We've got carbon number 2. That's this one. Carbon number 3. Carbon number 4. Carbon number 5. This is the one that's going to be reacting. And then carbon number 6 is going to be left out of the ring. So this is what's going to happen. So the carbonyl carbon is going to be reduced by this hydroxyl group. When it's reduced, that means it's going to gain that hydrogen and gain electrons, and it will become a hydroxyl group. It will be reduced to the carbonyl carbon. That's number 1. Will be reduced to hydroxyl group, adding hydrogen to the oxygen, right? Reducing it. And so what you'll have is it's a spontaneous reaction that happens in equilibrium. So since I haven't done anything yet, this is still a linear molecule, just fold it over. The equilibrium is between the linear form, which is really both of these, and this ring structure. So what you end up with is, here's, I'll start with carbon number 5, carbon number 4, carbon number 3, carbon number 2, Carbon number, oh boy, it's getting weird. Angle problems. Carbon number 1. Come on, carbon number 1. Right? And then, so here's carbon number 5. What's happened to carbon number 5? It used to have a hydroxyl group. But this hydroxyl group, this hydrogen, has now attached to this group, so it's just an oxygen that's left there. And that is attached to, I got kind of flattened, I don't know why, to carbon number 1 there. Remember, carbon number 6 is out of the ring here. It's just nothing's happening with it. So, this
is a single bond oxygen.
What? Yeah, this is a single bond now because it's a hydroxyl group. See what's happened? Just we've taken the hydrogen with its electrons, we've moved it over here. And so now this is just carbon single bond with a hydroxyl group. This is the, I'll put the hydrogens in. Hydrogen, this one, this carbon has a hydroxyl group. The hydrogen going in this direction. This one has the hydrogen group sticking out and the hydroxyl group sticking into the ring or up on the board. This has the hydroxyl group sticking out. I'll put that one in. So keeping track of our numbers here. This would be carbon number 1, which used to be a carbonyl carbon, but now it's just part of the ring. This is carbon number 2, 3, 4, 5, and carbon number 6 out of the ring. Now you should understand how that works, but you don't have to draw it like that. We simplify that quite a lot. Because you don't really, remember I showed you that picture of all of those, like the benzene rings and those ring structures where instead of drawing the carbons in, you just drew the corners and they imply corners? Carbons, we're going to do that. I just realized this picture right here. Your textbook has all these pictures, by the way, if you don't like my drawings. So here you are, glucose. See the shape of it there, it matters which direction that is facing. And so this is what we've just done. So they do explain this in your textbook. If you have trouble following this, check out their color-coded version of this. A little nicer done than mine. And they show you the final structure. This particular way that the folding has happened, this is a form of glucose. This ring structure is called alpha glucose. Because carbon number 1 there is now an asymmetric carbon. And that only ended up having that hydroxyl group pointing down like that because this happened to be pointing down when it was formed. Had it been pointing up, it would be a different isomer. You'll see. So, finally, sorry, I'm going an extra 10 minutes here, but this is so worth it, right? Yeah. To me. So let me show you an easier way of drawing this and show you the whole equilibrium. You get a break. Promise. Okay, so I'm just going to simplify this, redraw it, simplify. And I recommend drawing it this way, you really should. Now I'm going to try to get the angles to look that shape. It can be hard to do. I used to be really good at this on chalkboards, but I'm still not that good at it with a whiteboard. This is slippery, the right way. Easier with a pen. So, the corners represent oxygen with carbon. Of course, oxygen is not carbon, so I have to draw the oxygen in that corner over there. And up. Oh, maybe that was not going to work out well. Hold on. I'm striving to draw shapes. Take one drawing class. Oh, there. All right, trying for the shape there. So each one of those corners represents one of those carbons. So this is carbon number 1. Now remember carbon number 1, oh, I need to put carbon number 6 there. Out here. The CH2OH. And the hydrogen. I want to put the hydrogens in for this first form. So carbon number 1, we have the hydroxyl group pointing down. So in this particular convention of drawing, instead of drawing things out to the side, just draw the line straight up or down. Those are the choices of configuration of those groups. And so that means that carbon number 2 here, the hydroxyl group is down and the hydrogen is up, which is the opposite of this one. Where the hydroxyl group is up and the hydrogen is down. And here at carbon number 2, the hydroxyl group is down, the hydrogen is up. Okay. So this is the alpha glucose that I showed before. Keep track of the carbons. Remember this is carbon 1, 2, 3, 4, 5, and 6. applied in those corners. Now, if you don't want to put the hydrogens in, just don't draw a line to them. And then that's another shorthand way, and we will get to that shorthand way. So here's the equilibrium between the alpha glucose and then the linear form, 2, 3, 4, 5, 6. Oh, another chance to draw linear glucose. You can't have too many opportunities to practice. So we have we'll just call this linear glucose. It's still the same molecule. And now this formed because this carbonyl group, the carbonyl part was pointing down when the ring formation occurred. It could be pointing the other direction. If this were to flip in this direction, the carbonyl group was over there, then it would end up pointing up when it made this ring structure. Instead of pointing up with this, because the carbonyl was pointing up, it would have been stuck up, that oxygen. It's stuck up oxygen. So that gives us our other type of isomer of glucose, which is exactly the same as the first, except even if mine doesn't look the same, because there's something weird with my shapes there. It's a little weird. It's a matter of perspective. I don't have any. It looks like that shape. So everything else is the same. CH2OH, out here, carbon number 6 there. We have carbon number 5, the hydroxyl group is down. Carbon number 4, the hydroxyl group is up. Carbon number 3, the hydroxyl group is down. Here's the only difference, and that is carbon number 1.
The OH just pointing up.
The hydroxyl group is up. Everybody up? So this should be exactly the same. This is called beta glucose. The only difference is in that the location at the carbonyl carbon there. This is 1, 2, 3, 4, 5, and 6. The difference is that hydroxyl group gets stuck in that position. So these are asymmetric carbons. What kind of isomers are these of each other?
Structural.
Diastereomers. Diastereomers, yeah. Diastereomers. So in water, this is what you have, all three forms going back and forth. So the linear glucose is forming alpha glucose. The alpha glucose will open up and then it would form beta glucose. This is always forming, so they're all present all the time. That is how glucose is found. And this is all shown this way in your textbook, so you can take a look at that abbreviated ring structure. I put on the slides from a different textbook another explanation of it, just so you need something to follow. Okay, I have one with the pointing hand one. This is also useful. Pointing hand structure. So these two molecules are going to have a very different shape. If you build the models, you find that it makes a difference which way you point it. They just put that. It's weird the way they put that on there. One's pointing this way, one's pointing that way. I have lots of ways to show this. Alpha, beta. Okay. Here it again. With the carbons back in there, you can put the carbons in there, but you really shouldn't because it makes it messy. In a space-filling model, you can see what's sticking out here. All those hydroxyl groups are sticking out on the surface. So would you consider this molecule to be soluble or insoluble?
Soluble.
Soluble.
The sugars are all water soluble, right? Very polar molecules. All right. So you've been very patient. An extra time. Why don't you take a break? Take 10